Okay. So, chapter 7 goes along with chapter 5 and 6, except this time we are no longer trying to create a circuit. Okay? We are trying to reach out to every place without creating a circuit. Okay? So, in this chapter, we're going to talk about networks. Your vertices are now going to be called nodes or terminals.
It's going to be just for the rest of the class, like nodes and terminals?
I mean, I'll still refer to them as vertices, but you may see it as nodes or terminals. Okay? Your edges are now going to be called links. Okay. And this chapter's theme kind of goes right along with chapter 6. We're still trying to find optimal networks. So we're still trying to find the shortest way, the cheapest way. Okay. When I think about this chapter, I think about electrical lines, I think about gas lines and all of that kind of stuff. You've got this main terminal, okay, that then sends electrical lines out to your houses, out to businesses, and everything else. Well, it doesn't have to create a circuit. It just needs electricity to go to one place and go to another place and go to another place. So that's what we're going to try to do. So our goal is to connect all of the terminals. Do not make a circuit. And of course, we always want to pick the lines that are as small as possible, which makes it an optimal network. So these are the types of problems that you're going to see. The weighted graph represents a system of roads that connects buildings, and they're trying to put in fiber optic cable. Okay, each one of these numbers on your graph is how much it costs in millions to run fiber optic lines. Fiber optic is expensive, so they want to do it in the cheapest way possible. So, in order to do that, we're going to build something called a subgraph. Subgraphs are when the edges come from the original graph. So, if you have a line that connects C to D, you can use the line that connects C to D. If there was not one that existed, you cannot use it. We also are going to create something called spans. We will talk a little bit later about spanning trees. When we do a span, the graph must include all vertices. Okay. So all of your nodes or all of your terminals have to be used. So if we were creating a span of this graph that you're looking at right now, you must have all 5 vertices. You cannot skimp out. Okay? And finally, for it to be minimal, that means your total weight must be as small as possible. Just like we did the cheapest link algorithm and the repetitive nearest neighbor, you're looking for the smallest way possible to do this. Questions? Okay. So what we're going to do is we're now going to create some subgraphs and some spans. So we're going to start with subgraphs, and we're going to do all the subgraphs. So the subgraph is just a chunk of your graph. Okay. Example number 1 here wants us to do 4 vertices that have 6 edges. Now remember, your 6 edges have to come from this original picture. You can't draw new lines. So to create a subgraph of 4 vertices, I'm going to label this B, C, E, and F.
Does it matter what you pick?
Okay. It's going to matter in this one because if you do A, B, E, and D, you can only get 3 lines. You need to have 6 edges. So it's going to have to be the 4 on the other side. Okay. So again, 6 edges. Well, I have an original one that connected B to C, so I can connect B to C. I had an original one that connects B to E, so I can do that. E to F, F to C. And then you add the 2 in the middle, C to E and B to F. So this would be an example of a subgraph that has 4 vertices and 6 edges. We're going to do all the subgraphs, so I want to jump down to here. This time, I want a subgraph that has 5 vertices.
5 edges.
And 4 edges.
What?
Where are you getting 5 edges? It says 5 vertices and 4 edges.
Oh, you're still talking about the square one?
I told you we were jumping down here to do all of the subgraphs first. Okay. So, I need 5 vertices. Which ones do you want to use? Any 5 you want.
A, B, C, D, E.
A, B, C, D, E. Okay? So, we've got A, B, C, D, and E. Okay. Second criteria says, I want to draw 4 edges. I need to pick 4 lines from the original graph that I can draw to create a subgraph. The biggest thing is every dot has to be reached out to. There has to be an edge that goes out to every dot. So, what would you like to connect?
A to B.
A to B. Okay? There was one in the original, so I can use it.
B to C.
You said B to C. There's one here, so I can use it.
C to E.
C to E. Perfect.
Then D to E.
And D to E. That's a subgraph with 4 edges. Instead of doing C to E, you could have done B to E. Okay, there's multiple ways, again, to do this section. Example 3, over here, this subgraph. Why do I have 2 examples? We're just going to roll with it. Okay, example 3 on this side. Subgraph, this time we have 6 vertices and 5 edges. So I need all of my dots from my original graph. All of my terminals. A, B, C, D, E, and F. Okay, this time they want us to connect all of them with 5 edges, sorry. 5 edges. There are 2 lines that we always have to use. What are they?
A to B.
A to B. Why?
Because
that's the only line that reaches out to A. And D to E. Those 2 are givens. You can't do anything else because there's no other lines that reach out to those endpoints A and D. So those are 2 givens. We need 3 more to connect the rest.
Let's just do C, E, F, and C, F.
B, C, E, F, and CF. That works. Okay. The only difference between the subgraph and the span, notice the span just says how many edges you need. Why doesn't a span say how many dots you need?
You already
used all the vertices.
Your span has to have all the vertices, no matter what. So they don't need to tell you how many you have. They're automatically, every dot that you have in your original graph is part of your span. Now we need to connect with 5 edges. What'd you say?
I was just doing the same.
You can do the same graph that you have down here. Okay? Your subgraph of 6 vertices and 5 edges is also a span. We could have done something different. So there's A, B, and D, E, those 2 that I have to have. I can go EC, BF, and CF. And that's still a span with 5 edges. It has all of your dots and 5 of your original edges. So both of these graphs for this one and this one are the same thing. And then finally, this one, again, it's a span, so you should automatically have all 6 dots. E, E, and F. This time they want us to connect with 6 edges. So what would you like to draw?
You gotta do A, B.
You've got to do A, B, and D. Those are given. Said E to F. You said what? FC,
VC.
BC.
Yeah.
You want to do what? You can't do AD. There's no line that connects AD from the original.
That would make it a circuit too.
Right, that would make a circuit too. D to E.
Whoa.
Even though that still creates a circuit there, C, E, and F.
So that doesn't work.
That's fine. Your only thing here is you have to have lines that were already originally there. There was no line that connected AD, so that was a no-no. Okay, but you had a line that connected C to E, so that is absolutely fine. Question.
Can I go use the bathroom now, please?
Not in the middle of my notes, sir.
I can't. Like, it's actually an emergency. Like, it really is. It's like,
Give that man a bottle.
please.
By all means, my friend, but whatever you miss, don't ask.
Give that man a bottle.
Okay. The last thing we need to talk about in this chapter is trees. Okay. Your definition for a tree is a network. And because it's a network, that means it must be a connected graph. Which means we can't have separate pieces. Remember, we already talked about connected graphs. Everything has to be reached out to. There cannot be 2 separate pieces or 3 separate pieces or even an isolated vertex. It can't happen. Also, they have with no circuits of any length.
So that last circuit we did wouldn't fly in this one.
No, it would not fly. It is a span, but it is not a spanning tree.
Whoa.
Okay.
Must be a mix.
Okay, so because we can't have circuits of any length, we cannot have any loops. Loops are out, because remember, loop is a circuit. Okay, so let's take a look at this. Look at graph A. Would you say that that is a tree or not?
No.
Yes.
No.
I mean, everything is reaching.
Yeah, no, yes.
Yes.
It's not a tree.
Yeah, I was gonna say, it's
Why?
Why is this not a tree? It's not connected. I've got 2 separate pieces. This is not a connected graph. You can't have 2 separate pieces. This is no.
Now I feel that we got it right. Look.
I just got done telling you it had to be a connected graph. And it could not have extra pieces. You want to shush me again, and there's the door. I am an adult, and you're not going to talk to me like that.
It wasn't like,
No, no. Take a look at graph B. Would you consider that a tree?
Yeah, that's a tree.
That is a tree. Everything is connected and there are no circuits. What about C?
No, that ain't no tree.
No. Even though it looks like a tree,
just a circuit.
what you all think, but I've got this circuit right here. That's a no-no. Can't have that. What about D?
Yes.
No, that ain't even no tree.
Why is it not a tree?
Because ain't no connected graph.
How is it not connected?
What is it connected to?
Itself? Everything that is there is connected by a line.
So if everything connected is a tree. Then it's a tree then.
Yes, this is a tree.
It's like a star.
It is a star. But it's considered a tree because every dot is reached out to with a line without any circuits. Take a look at graph E. This one is a tree. It's kind of like your Y's above it, but they're put together. Okay, so that one is a tree. What about F?
No.
No, you've got a ton of circuits in that one. Okay, you've got this top circuit, you got one in the middle, you got one in the bottom, you got a big, huge one that goes the whole way around. That is one mess of a tree, or not a tree, but it looks like a Christmas tree. Take a look at G.
Yes.
No.
No, it's a yes.
Yeah, it is a tree because it ain't no circuit.
Oh, no, yeah.
It's not a circuit because this is not connected here. If you follow this around, it ends up here instead of going back home. So yes, this is a tree. And finally, H.
Yes.
Yeah.
It's gonna be a no for me.
It is a no.
Right.
Watch. Even though you can't tell that this is a circuit, if I start here, I follow this around, and it goes back. Okay. So be very, very careful because sometimes they will twist them so you can't really tell that there is a tree or a circuit there or not. So be very, very careful. Okay, so we've got some discovery observation questions. First off, we want to look at the graphs that are trees. Is there a relationship between the total number of edges and vertices in the trees? So if I go back to each one of these graphs, how many vertices are in this graph B that is a tree? We're only looking at the ones that are trees. I've got 11. How many edges are there? 10. Take a look at this one. Vertices. 6 edges.
Wow.
5. Okay, go down here. Vertices. 7. 6 edges. G. 8 vertices. 7 edges. So what's my relationship here?
N minus 1. So no, I'm playing.
Well, B minus 1. Your edges are 1 less than your B. Okay. So if I tell you you have 12 vertices, how many edges should you have? 11. Okay. That happens every time. So your relationship, vertices are 1 more than edges. Or I can say in reverse, edges are 1 less than vertices. That will always happen if you have a tree. That is something that's going to be very, very important when we get to our always, sometimes, and never section.
When you saying special term, does it mean equation?
No, special term means we've talked about terms before with graphs. There was a certain word that we talked about. Okay, so is there a special term you can use to describe the edges used in these?
Path?
A network.
It's something we talked about in chapter 5. Who was one of your key terms?
No.
What was
Began
chapter
with a
5
B.
again?
A B?
Began with a B.
That's funny.
Bugs Bunny.
Next list.
What's that, dog?
A limnicon.
Malignacol? What is that?
I don't know. I thought you would know.
BR?
Root.
Brick.
Not brick. What?
Brute force.
I swear you were gonna say it.
Brandy.
It's so BRI.
Huh?
It's BRI.
Uh-huh.
Class.
Bridge.
What?
Bridge.
Bridge.
It's a bridge. Okay? Each one of these lines in a tree is a bridge. If I erase this line, it disconnects my graph. So any one of these lines in a network, in a tree, is considered a bridge. Okay, if I remove it, it disconnects my graph. That wasn't too bad like pulling teeth. Okay. All right. Spanning tree. This is a specific type of tree. So, a subgraph. Of a network. That connects all vertices. And has no circuits. So the easiest way that I can tell you to draw a spanning tree of an original graph is to think about what we just talked about. First off, it says all vertices. So when you draw yourself a spanning tree, and I know I did not leave you a lot of room. There's enough room that you can probably fit one of these on there. We're going to do a couple up here so we can talk about it. Okay. We need all vertices. So you need A, B, C, D, and E. Those are all of your dots from your original graph. Okay, think about the observation we just made. If I have 5 dots, how many lines do I need to create a tree? 4. I need 1 less edge than I have dots. So I need to connect all of these dots with 4 lines from my original graph. Any 4 lines you want. What do you want to connect?
Or A to A.
Okay. You said B to A. Okay.
Don't we have to have B and E though? I mean,
Oh, I'm tripping.
Do we have to have what?
don't we have to have D and E?
Not necessarily, because you can reach out to E from C.
A.
So.
Go to C.
Go to C from where?
A.
Okay, so A to C. That's 2 lines.
D.
You said from C to D.
Yeah.
And then down to E.
Yep.
Move it on up.
That's a spanning tree.
Question mark.
You gotta connect all of them.
Okay, you just have to connect to all of your dots with lines from your original graph. So what I mean by that is you can't connect B to D because there was no original line there. And again, because you have 5 dots, you always have 4 edges. If there was 7 dots, you'd have 6 edges. There's always 1 less edge than dots. So let's draw another one. You don't have to put this on your paper if you don't have room. A, B, C, D. Let's do the same thing, but with some different lines. What would you like to connect this time?
C to E.
C to E, okay?
B to D.
A to D, okay?
C to B.
C to B, there's 3.
A to B.
Stop connecting now.
A to B, there's 4.
Go for the day.
Notice that there is a Euler path that connects all of these dots. I can start at 1 and connect without lifting my pencil. I can do the same thing here. So if you were told that you have dots and a Euler path that connects them all, yes, it is a tree. Okay. Questions? Okay. So these are the properties that you're going to use for your always, sometimes, and never. This is the worst part of the chapter. Okay. Property number 1 says, if you have 1 and only 1 path that joins 2 vertices, you have a tree. Property 2 says, if every edge is a bridge, you have a tree. And property 3 says, if you have n vertices, then you should have n minus 1 edges. In other words, your edges should be one less than your vertices. So let's see if we can answer these. Number 1 says, my graph has 4 vertices and 3 edges. Would you say this is always, sometimes, or never?
Always. Oh, yeah, sometimes.
Why would this be sometimes?
Because you can have 5 vertices and 4 edges.
You can't. It says you have 4 vertices and 3 edges. You can't change the numbers.
Oh.
But I agree with sometimes.
I don't know.
What does this not tell me?
If,
Take a look at number 2 compared to number 1. Number 2 is going to be an always. What does number 2 have that number 1 does not?
Not connected.
Oh.
This tells me connected. This doesn't. So I could have one that's completely connected, like this. That one works. But I could also have one that's not connected, like this, where you have an So, number 1 is a sometimes. On your test, when you have sometimes, you're going to have to draw me a picture of one that is a tree and one that isn't. So you would draw me something like this and something like this. So, your keywords are going to be connected. That tells you that it's a tree. Bridge. That tells you that it's a tree. Take a look at number 3. We have 5 vertices and 5 edges.
Never.
Never. My edges always have to be one less. So that's a never. Take a look at number 4. 5 vertices and 4 bridges. That's an always. Again, your keywords are connected and the fact that you have bridges. Bridges means no circuit, so that makes it an always. Okay, so look for those 2 words. Need to move that. Number 5, 10 vertices and 9 edges. That one's going to be a sometimes. I'm not going to make you draw that because you definitely don't have enough space for 10 vertices and 9 edges.
Never.
6, you said never. Whatever that was. Never. You can't have more edges than vertices. 7, 12 vertices and 11 bridges.
Oh, always.
Always.
Never see that.
Always. And I agree with the last one. Never. Never. What does it mean for a dot to have a degree of 7?
It
And
has
that's
7
7
edges
lines.
for
It has
every
7
vertice.
lines, and every one of those dots has 7 lines. So this is a holy cow, no way. Okay? Holy cow, no way. Never gonna happen.
Anybody else who get like super sleepy?
Good thing we just have the back of that page to do, and I'm done for today. And we will finish the rest tomorrow. So we're almost done. And then you can be sleepy all you want.
Thanks.
Can I get you for like 5 more minutes? Like, do you need to get up and do some jumping jacks for a minute? Like, run around the room, smack yourself in the face a little bit? Huh? No, because multiple edges will create a circuit. Because if you've got 2 dots and they connect here and here, that's a circuit the whole way.
Turn around.
Okay? Take a look at the top one, 1A. Would you say that this is a spanning tree or not?
No.
No, why?
Circuit.
There is a circuit. So, since there's no spanning tree, we're going to draw ourselves one. D, E, F, and G. How many edges do I need to create a tree in this graph? 6. I have 7 vertices, which means I need 6 edges. So, we need 6 edges from the original graph to reach out to all these dots. What would you like your first edge to be?
A to E.
A to E. A to E.
You
Gotta
see
have
that?
CG.
You gotta have what?
Yes.
You've gotta have CG. There's nothing else that reaches out to G. So that's 2.
Yes.
E to F. Okay, there's 3. F to C, there's 4. A to B, there's 5. And you said what? B to D, there's 6. Done.
Oh, yeah.
Did it have to be those 6 edges?
No.
No.
I'm going back when I was a tree.
She's gonna be like, what?
All right.
What you talking about? Okay, take a look at 2A. Is this graph a tree?
Yes.
Yes. So guess what? We don't need to do this. It already is one. Okay, this leads me to property number 4, which is calculating redundancy. This equation will tell you every time if you have a tree or not. Okay, so redundancy equals the difference of edges and vertices plus 1. So in mathematical terms, it looks like this. R equals E minus B plus 1.
So it's basically the same thing as you started on.
Yes and no.
Jeez.
When we get into tomorrow's stuff, this will make a little bit more sense. Okay. So actually, let me back this up, Trey, and maybe this will catch you. So if you would go back to here, okay, we would do redundancy equals how many edges are in this original graph?
The original? 7.
7. 1, 2, 3, 4, 5, 6, 7, 8. How are you counting 7? 1, 2, 3, 4, 5, 6, 7, 8, 9. Edges. So 9 minus how many vertices are there?
7.
Gentlemen, you should be paying attention because when you have questions later, I'm not answering them. Stop talking while I'm teaching. There are 7 vertices plus 1.
8. Oh,
What
yeah.
does that give me? 9 minus 7 is?
2.
Plus 1 is?
3.
3. Okay, so that tells me I needed to remove 3 edges to make a tree. Well, I only needed 6. I had 9, so I got rid of 3. So that's what it tells you, okay? Okay, so if you end up plugging this in and you get R equals 0, that means you have a tree. If your redundancy equals 0, that means you have a tree. If your redundancy is greater than 0, that means you have not a tree.
If it's less than, does that mean graph is this one?
You will never ever have less than. If you plug in your number. So, if your redundancy is positive, something that is greater than 0, it tells you how many edges needs removed. So, your redundancy tells you how many edges needs removed. Thinking about it, if you get a 0, that means you need to remove 0 edges. If you get 2, you need to remove 2 edges. Okay, it doesn't matter what 2 technically that's in a circuit, but you're going to have to remove 2 of them. So this will tell you how many, it just won't tell you which ones. Your last example for today. So how do you find a spanning tree? Your goal is to remove R edges, which means we need to break up your circuits. This is the key. Our goal is to break up our circuits. We do not want to remove any edges that are already bridges. So we're going to first calculate how many edges I need to remove. Remember, R equals E minus B plus 1. So how many edges are in my graph?
There's 8.
There are 8. 8 edges. How many vertices?
8.
8. plus 1 gives me what?
One.
1. I need to remove one edge. I need to remove one edge from my circuit. Where is my circuit? This is my circuit. I can remove any one of those 3 edges. I can remove C to D.
That's what I said.
Or you could remove C to H. Or H to D. Doesn't matter which one. You just need to remove one of them to break up that circuit. Questions? Okay.
Does that mean there's 3 possible spanning trees?
Yes. And we will finish talking about that tomorrow.